back to proton NMR. We talked about chemical shifts. Now let's talk about integration. So that's the relative number of protons under each peak. Here is BHT. Yet again, we've looked at the carbon-13 spectra. Here is the proton spectra. Here, again, we've got our CH3s, not that deshielded. They're about 1.5, so they're a little bit deshielded by the rings, separate out here. This CH3 is a little more deshielded by this pi bond here. We'd expect it to be around 2, and it is. We've got a peak here. It's hard to see. It's right on the 5.0 line. That is from our hydroxy, and our peak around 7, that is exactly where aromatic protons show up. And so that is where we see those two hydrogens. And so what we're looking at here is this curvy line that goes all the way over the spectrum. What is that? That is measuring how many protons are under each of those peaks. So, and this is kind of the visual aspect, is kind of a throwback to how NMR used to work back in the old days. But long story short, if I take the height of that little step function, so that distance versus this distance versus this distance versus this distance, the computer is going to do all this for us. But if I look at all those heights, what I'm going to see is a ratio of 2 to 1 to 3 to 18. And that's because of how many protons I'm looking at. There are 2 purple aromatic protons, there's 1 OH, there are 3 of the bottom methyl protons, and there is fully 18 of the terp-butyl CH3s. Okay? So the computer does all the measuring for us. It puts numbers down. Those numbers, we usually have to set one of the numbers and then say, okay, I think that this is, like I might put my cursor here and tell the computer, I think this is 2H. And then the computer say, okay, well, if that's 2, then I find this one to be 1.01, and this one to be 2.99, and this one to be 18.14, or something like that. They're usually very close to the integers that they should be, but we get a relative amount. We get relative numbers of peaks, not just absolute truth coming out of the machine.
Now let's talk about splitting. So again, let me set the scene. There's a little proton here, a little nucleus with a little spin, and that spin is now here aligned with this big magnetic field, right? And so the question is, how much magnetic force does that little hydrogen, that little bar magnet, I like to think of it, feel? What force does it feel? It turns out that that force is affected by other atoms around it, other little bar magnets around it. So for instance, this little green hydrogen is pretty close to that blue hydrogen in space. And so that little bar magnet is going to affect that little bar magnet. In what direction? Well, remember, we're dealing with more or less close to 50-50 splits are going with the magnet or against the magnet. So this hydrogen could be aligned with the magnet, in which case this blue hydrogen would feel like this big shift plus this little field. Or the green one can be aligned against the magnet, in which case that proton would feel this big field minus this little field. And so what once was one frequency in NMR is now going to look like 2 peaks, because it's equally likely that that neighboring proton would either give it a little more magnetic field or counteract a little bit of the magnetic field. And that's called splitting. Now, you might say, what about this proton? Well, this proton, just like this proton is affected by this proton, by the same way that that's affected by that. So we're going to call this pair of peaks a doublet. And so each of these protons, we would say, is split by its neighbor. And so each of them will be a doublet. Well, 2 doublets in this spectrum. And we'll talk about this more later, but the distance between these peaks are going to be the same, because I guess A affects B just as much as B affects A, right? We all affect each other in this world. Let's look at this alkane. Just like before, neighboring protons are going to affect each other. If we look at this CH3 first, the CH3 is split by 2 equivalent protons here. So 1 carbon over these H's. These 2 are identical, and so these hydrogens, which again would show up as 1 peak usually, now are going to be split by both of these atoms. So if something is split twice, it's almost like flipping a coin twice. You end up with heads, 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 tails, tails, heads, tails, tails. Right? So your distribution is going to look like a triplet, what we call a 1 to 2 to 1 triplet, right? Where this peak is 2 and that peak is 1. If I look at these green protons, here I have 2 protons that are split by 3 neighbors. So over here I had 3 split by 2. Now I have, in an equivalent way, 2 split by 3. And it turns out that that will look like a quartet. Remember, I started off with 1 peak going to 2, going to a doublet, because it was split by 1 hydrogen. If it's split by 2 hydrogens, then I go to a triplet. If it's split by 3 hydrogens, I go to a quartet. If it's split by 4, it's a quintet. If it's split by 5, it's a sextet. So, and on down. So in general, if I'm splitting by n equivalent hydrogens, then the peak itself is going to be split into n plus 1 peaks. So we're counting neighbors and then adding 1 to see how many peaks we have.